What is the most used man-made material on Earth? You guessed right, it's concrete. Look around. It's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future.
And welcome to another episode of the Concrete Logic podcast. And today I have another returning guest, Bill Kulish with Steelike. Bill, did I say your last name right? Should have checked with you before.
Yes, you did.
All right.
Yes, you did.
All right. He's going to get us up to speed on ultra high performance concrete and then remind me what that is, because we haven't talked about it for, I think he was on episode 34. And that was over 10 months ago. So I need a refresher, Bill. But before we get started, just a reminder, everybody, the way this podcast works is it's a value for value. So if you get some value out of this podcast, all I'm asking you is to return the value. And you can do it in several different ways. One is share the podcast with a friend or a colleague or whoever you think would get something out of it. That's one way. The second way is if you go to our website, there is a microphone button on the bottom right-hand side. If you click on that, you can actually record a voicemail to me. If you could go on there, if you've got a question, an idea for a podcast, hit that and record it, and it'll send it to me. So that gives us an idea for podcasts and podcast guests. So that is great if you could do that. And then the third thing is, again, back on the website, upper right-hand corner, there's a donation button. You click on that. And like I said, if you get some value out of any of the podcasts, if Bill says something to you today and you're like, holy cow, I didn't know anything about ultra high performance concrete. Now I'm an ultra high performance concrete guru, or maybe not, who knows? But anyways, if you click on the donate button, you can donate any amount, and any amount is appreciated. It just helps us keep this thing going. With that, Bill, did I explain that?
Very clear. Very clear. I will be clicking one of those buttons, the last button, when we're done.
Oh, appreciate that. Bill is with Steelike, and Steelike is ultra high performance concrete. What would we call your company?
A supplier of the material.
Okay.
Yes.
Inventor, right?
I'm the inventor. I have many letters, but basically we're a small company. It's my wife and I. My wife's the CEO. She left a cushy job at DuPont, believes in the material enough, and that was back in 2018-19, and we've been charging full steam ahead ever since. But I invented it, designed it, and I used to say every bridge project we've exceeded 50, and it's a good problem, but I had to let go of control, so now I have a good support team that is often on the project when I cannot get there.
Yeah, that way you can do more, right?
Yes.
Yeah. Okay, Bill, remind us what ultra high performance concrete is and what separates it from normal concrete.
Absolutely. I'll start by just changing one letter. So it's not the letter, but ultra high performance concrete. It's actually ultra high performance composite. It does, of course, have similarities with concrete, but the largest aggregate is less than the diameter of a human hair. So where traditional 5K mix, 5,000 PSI mix might have a chunk of rock, for every chunk of rock, I'm replacing it with thousands of grains of different types of sands, different shapes, different mineral contents. So that's one of the big differences. The other big difference is it's a non-contiguous pore structure. So there's no channels left when the material cures and hydrates. And because of that, there's no way for water to get in. There's no way for water to get out. And that also means that chlorides, salts, de-icing agents, they can't get in, period. The other thing is with a true UHPC, and I say that stuff because you can Google it and you'll see companies offering unicorn dust to turn regular concrete into UHPC. It's frustrating with my colleagues and other suppliers, but a true UHPC, and there's really a handful of them globally, A true UHPC, the more you freeze and thaw it, the better it gets. So you freeze and thaw Steelike 600 times, it goes from 100% to 104%. There is very little shrinkage. I'm not a mechanical engineer, but I surround myself with people smarter than I. And I said, here's my number. What does it mean? 427 microstrains. And they're like, blah, blah, blah. And then I said, what does that mean? Give me a football field. If I make something over a football field, how much is it going to shrink? It's going to shrink about 8 inches. So there's the translation from science to just something we can all wrap our head around. Then we get into other benefits. Quite often the big focus in our world, in your world, Seth, is compressive strength. I want compressive strength. It's really high compressive strength. Having really high compressive strength only is similar to going to your kitchen cabinet, pulling out a porcelain plate, which might be 50,000 psi, and dropping it on the ground. What does it do? It shatters. It's brittle. So UHPC is going to be brittle because it's extremely high compressive strengths. On average, it's all time related, temperature related, but we're always over 21,000 in 28 days at normal curing temperatures, 72 degrees. You can autoclave Steelike and it'll be over 50,000 psi. Yay. Who cares? You're not going to autoclave a bridge. So back to the real world. The material does have really good compressive characteristics. More importantly, with that compression, with UHPC, there's freeze-thaw, abrasion resistance, chloride resistance, tensile is huge. The tensile properties of a true certified UHPC are remarkable to the extent that you'll actually get strain hardening. And I'll stop rambling in a second. I tend to get excited with your podcast, but you start to put a load on something, it cracks. You get your first visual crack. With normal concrete, you may get a couple seconds and then you get catastrophic failure. With UHPC, you get your first crack. It may be a visual crack, but there's millions of cracks occurring because of the metal fibers in most cases. Those metal fibers redirect the beginning of the microscopic cracking. The cracks are so small, they're watertight. We are talking invisible cracks within reason. If you look at it under an electron microscope, you would see things, but you would see things with any material you look at. After that first crack occurs, the fibers, the micro rebar, these half-inch needle high tensile fibers start to carry the load of the stress. But then it goes back to the concrete, and eventually a fiber slips, and then it goes back to the concrete. So in closure, you're doing a test, the strain goes up, and for those that can't see me, I'm just moving my finger upwards. Then you get your first crack, and it comes down. Then it goes back up. Sometimes it exceeds the force that cracked it. Strain hardening, like steel. Then it comes down, it goes up, so you get a sawtooth, and then a very gradual, slow failure versus catastrophic.
Got it. It's not truly concrete. What's in the composite?
The composite has a lot of similarities with concrete, and everybody in the industry calls it concrete. Nobody wants a composite driveway, so we like to push everything into big categories, which makes sense to me. What we have and I'll speak to steel, which is a true certified, vetted, tested UHPC. What we have is a very high binder content. Ironically, because many of those binders are post-industrial waste, we actually have something that has a lower carbon footprint overall. When you factor in the life cycle cost, you encapsulate something, a bridge, the deck is worn out, the salt's got in, the steel's starting to get attacked. You clean it up and you put down let's just say a 2-inch layer of UHPC, you're now fossilizing that bridge. Because there's no big aggregates, there's extremely little air. Because there's so much binder, not all of which is cement, there's so much binder in there that it's sticking to everything. And you put all that together, and the answer to your question is, yes, there's some unicorn dust, which I'm not certainly going to go into the exact recipe. But for the most part, it's over 40% binder, 55% of the right aggregate, very little water. Average water cement ratio is 18. I say average because when you do an overlay, it might be 16. Much less water, which means what is what you get. There is no creme. There's no cream. You do not trowel UHPC. It's self-leveling, self-consolidating. It's a composite. But for this podcast, we can certainly call it ultra-high performance concrete.
Okay. Yeah, to explain what it looks like, because I've seen your videos that you post on LinkedIn. It's, I think before we try to explain this, but I don't want to call it like, it comes out almost like if you were squeezing a toothpaste tube and watching it come out, something like that, or out of a caulk gun, the caulk coming out of that. It has a whole different look to it than concrete. And then when the one video, you stuck your hand in it and moved it around, and it just stayed together when you were moving it around, didn't separate. So it was like almost like taffy was getting pulled, is what it looked like to me.
That's a great definition. And I enjoy speaking to people like you because you have construction knowledge and background. When I make you smile or take question to what you're watching, I've achieved a big part of my goal from the beginning of the creation of this material. There's some really cool words to use that are just statements of science. Non-Newtonian fluid, thixotropic properties. If you take enough starch and you put it into water, we've all seen videos where you can run over it. If you stop, you sink. So this is a solid and a liquid at the same time. It comes out the chute. As long as the material is moving, whether it be from discharging, mixing, slapping, flowing, it's a liquid. Once it stops moving, it's the closest thing to a solid you can imagine. If you took your fist and punched it as hard as you could, you would hurt your hand. But if you put your fist and you just slowly let it go, it would sink in like quicksand. That's a big part of the advantages of it. It's more dense than water, so it'll displace water. We were doing an all-aboard Brightline project in Florida, and it had poured massively. All the joints that we were going to be connecting were full of water. We started pouring on the low side. Nobody was allowed to touch it. And it just displaced all the water. And by the time we got to the high side, clear water was coming out, and we had UHPC throughout the joint.
Yeah, I've done that with regular concrete, but I won't tell you what job that was. It was a long time ago. And we got caught in a downpour, and it filled up a beam. And so we pushed the water out with the concrete. Yeah, that's cool. So you hit on it, the type of projects this UHPC is on. It's normally, I see the videos of bridge projects, and you're either repairing, it looks like you're repairing a section of it, or like you said, an overlay. Is that normally where you apply your product?
As we speak today, yes, that's the majority of what it's used for. When I hopefully come back and do another podcast in a couple months, there'll be a whole bunch of other things that I can then describe. I can tell you that all good UHPC is fantastic for preservation, restoration, repair, impact resistance, weatherproofing. You're not going to see, at least in the United States, you're not going to see too many bridges or highways made completely out of UHPC. There's an over-engineering aspect to everything, Seth. And just because you can do something doesn't mean you do. It's got to be used at the right time. It's a much more expensive material, but its life cycle costs are over 75 years. So if you're building a bridge today and you're going to bury it under asphalt, it's sad to me. I'm not anti-asphalt, but asphalt has unintentional planned obsolescence. You're going to be back out there patching holes in a couple years. If you do a UHPC overlay and you don't put asphalt on it, the life cycle cost can go over 75 years. It's impervious. Salt, it doesn't recognize chlorides. If it's waterproof and salt and water can't get in, there's nothing to freeze, and it's going to preserve and encapsulate or fossilize any existing chloride damage to the rebar. So as long as that rebar is still mostly intact, you're wrapping it with a material that just is going to put a membrane on it that's going to stop it from ever being exposed to oxygen and water, / rust.
Yeah. Yeah, it'd be nice if we didn't have to deal with those guys every summer repairing all those asphalt roads, right? On the highway and on the bridges.
Yeah.
Yeah.
Oh, God. Think of green, reducing the carbon footprint. I get it. I'm with it 100%. Making Portland cement requires a lot of fossil fuels. I was watching a documentary the other day on the water cost, the water footprint. And for the average bowl of curry, it was 2,000 pounds of water. And I'm like, what the blood? How's that possible? And they broke the thing down. I recorded it. I watched it over and over again. It had potatoes in. It had carrots in. And all of those things require such an incredible amount of water. How we look at the actual real footprint also should be looking at the life cycle cost. If it takes, and I don't have this number calculated today, but if it takes 20% more, because I mentioned the binder ratio is higher, to make a UHPC, if it takes 20% more Portland cement, but it lasts 50 times, 100 times longer, it's almost a net return on your investment. Yes, you put in a material that may have a higher carbon footprint, but at year 30, you're not ripping it out and replacing it. Asphalt, petroleum-based product, it gets hot in the summer. It's wearing tires down faster. Air conditioners have to be turned on more. There's just so many variables when you truly look at life cycle costs. And again, I'm not denying that UHPC has a bigger input or effect, but I will definitely respectfully stand toe-to-toe with anybody that says, oh my God, it's real bad. You can use 40 to 50% less of it. So you got a material that has less carbon footprint, bringing trucks to deliver it, bringing trucks to remove stuff, getting rid of more earth than you need to when you can remove 40% less earth, putting down 2 inches on a bridge that's going to most likely last over 75 years, it really starts to make sense. And at year 30, 25, 30, that higher carbon footprint from day one has broken even with the recycling cost. Look at repairing a bridge. You have to factor in inflation. Rebuilding that bridge in 30 years is not going to be what it costs today. So it's just some overview stuff.
I totally agree. We're getting too wrapped up on, I think, the CO2 thing and not missing. We're missing what you're talking about. To me, the thing that pops in my head is you could either put all your money down like a deposit up front and make that investment now, or you can go with something cheaper that you pay month to month, and then eventually you're going to have to pay a whole replacement 5 years down the road. That's the type of material that we're using out there right now because, I don't know, we just like to spend money.
Security.
Yeah, job security. We got to make sure those asphalt guys stay busy. So, yeah, I think you guys caught up and a good refresher on what UHPC is and where it's being used. Did you want to talk a little bit about what you've done lately that you messaged me on LinkedIn about?
Sure.
So you can clue me in, because I was sharing with you before the podcast some of your stuff. It was over my head. So you said you did the first UHPC overlay that did not require profiling. What is that?
Yes. Okay, so in Oregon, we did the first UHPC overlay in Oregon. An ideal state, every part of the globe is, whether it's hot, cold, freeze-thaw. I mean, we're talking about salts, chlorides, freeze-thaw. Really good place for UHPC to shine above the way it shines even in Florida. But that's salt, right? There's oceans around it. So there's very few places where it doesn't have advantages. In Oregon, it had more of an advantage. So traditionally with overlays, you remove the decay. Think of the dentist. You get a cavity, you go in, they don't say, rip it out, put in a new tooth. They get rid of the decay if the tooth has enough structure and then they put something over it or inside of it to keep it alive for another period of time. Overlays are exactly that, Seth. You come in, you remove the decay. Generally, they hydrodemo. They might shot blast, but they hydrodemo to get rid of old stuff. Most often, it doesn't go all the way down to the bar, but every now and then, and there was in Oregon, they got to a point where the decay was down and under some of the bar was still intact, but it was a pool that was holding salt and water. In a couple of years, it would have required replacing the bar. In this case, it did not. And they take off about 2 inches, 2.5 inches average. And then you come in and you place the material. And I mentioned the word thixotropic. When you give Steelike or UHPC energy, it wakes up again. Think of it as cold lava. It's liquid steel, but cold lava, right? Lava is flowing. If it was hot lava, it flows and then it freezes and it becomes hard. There's nothing you can do. If you could keep it hot, it would keep flowing. In this case, the material is cold, relatively speaking. You place the material, I told you it's self-leveling, self-consolidating, but there's no flat bridge that I'm aware of that I've ever worked on because it has to have some kind of an arc, a curve, a dome, something to allow the water to drain. So this particular bridge had about a 2% crown. It went up and it came back down on this left and right-hand side. We were able to come in, lower water cement ratio, as I mentioned earlier, for an overlay. The thickness of that is closer to your toothpaste analogy, almost like a yogurt. The material was placed down, and then all of us, meaning all the suppliers, we put a vibrating truss screed or a vibrating screeding machine right over the freshly placed material. It vibrates, but it only vibrates the amount of time the mechanical device on the screed is touching the material. What happens when you vibrate Steelike? It becomes liquid again. But as soon as you go over it, it's no longer vibrating. It becomes a solid again, or a semi-plastic material, i.e. the whole bridge could be covered, even though it had a dome, a pitch, a crown, and the material didn't just flow off the sides. So it's a paradoxical thing. I'm telling you it's self-leveling, but I'm telling you that it'll self-level to a point, but then it'll stop self-leveling. Normally, that whole process has to be done, everything I mentioned. What we were able to do was, and it was because of this incredible contracting the contractor was amazing. They embraced the differences of this material. Sometimes we get contractors saying, I've been doing this 20 years. You're not telling me anything. And the problem is it's a composite. So they're trying to treat it and project it as if it's concrete. And then they get red in the face and they get pissed off and the material's defective. It doesn't happen often, and we've never failed a project. It can be really frustrating. These guys embraced it, and we did a rehearsal. And we did a full-scale mock-up, 20 feet long, 10 feet wide. After we'd spent 2 days doing that, we hit the actual live bridge. So it's 4 lanes with 2 shoulders. Traffic is going by on one side, and they close the other side. And we come in with, in our case, our method is a ready-mix truck because we can make 7 yards of material, which won't impress you, but 7 yards is a lot to mix of UHPC in a ready-mix truck. You add the water after you add the powder. So if you try to put more than 7 in, it would just start coming out the chute. That's the limitation of 7 yards. We serpentine the material down. They vibrated it with a vibrating truss screed, immediately sprayed it with wax to eliminate tarping. And to everybody's happiness, the state came back the next day and said, you don't have to profile this. The specification said it has to be within an eighth of an inch over every 10 feet. So you couldn't have a half-inch bump or anything over a 10-foot area. And we kept within that eighth inch. So the only thing and that's called profile, and I know most of you guys know, that's profile. That's where you're trying to shave off the high spots and get everything flat. They didn't have to grind the bridge. The environment was happy. Traffic was happy. They were literally driving on this thing a day after it was placed. And it was cold. It wasn't like we had chemicals and heat, Seth. And all they did is put in ruffled potato chip grooves, 1/8-inch grooves running longitudinally. And that was just to avoid hydroplaning, to give it a little more traction.
Okay. That sounds awesome. One thing I heard you say, did you say they put wax over the top of it? Is that for curing?
Yeah, a curing compound. Wax is a beautiful thing. You don't want to be using solvent based, blah, blah, blah. You just want to put a membrane over this material. There's very little water. There's such a great surface area that if you don't tarp it, normally the tradition is to tarp it. We simply have a design in our mix that allows it to avoid having a tarp. Now, we may use it if it's 95 degrees, sunny, and windy, but if it's no wind and within 40 to 80 degrees, we've been able to, with contractors, when I say we, the contractors, they're the guys doing the work. We're supplying the material. We're technically supporting them, guiding them, and mixing the material. Once it comes out to shoot, it's on them. But again, we guide them based on what we've seen other contractors do. You put this stuff down, normally you got to tarp it. The challenge with tarping it is you're hiding things. So you put the tarp down. If it's too soon, it can sink into the concrete. I have pictures of where they pull the tarp off the next day, and it's just wrinkled and crinkled, and there's then they go and they have to profile. They profile, but it dipped down so much. There's low spots that they cannot even put grooves in. So we simply, with the right contractor, using the method that we've reproduced a couple times, we can eliminate all of that. You put the material down, you vibrate it, you spray it with a curing compound, and you're done. What is what you get.
Yeah, so that aspect of the curing, or do you need it? Is it the same as since it was cold weather? Do you need to blanket it at all, or like regular concrete?
Yes, sir. At the everything with UHPC, mine specifically, heat. It loves cold when you're mixing and placing it. It loves heat after you placed it. We did a girder for a federal organization. They steamed it at 130 degrees Fahrenheit, and in 7 hours, it was 14,000 psi, which means if you're a precaster, you could put my material into a form, 7 hours later, demold it, do another one. You could do 3 a day if you wanted to. That was because it had extra heat. If there's not heat, obviously, the exothermic reaction, when it's cooking, when it's creating, crystallizing, if it loses more heat than it generates, Seth, you'll get there, but it just takes such a long time. We wanted to trap any heat we had because it was like 55, 60 degrees. At the end of the day, it was a sunny day. So we let everything get as warm as it could with the sun. It was going to drop to 40 degrees. Then they put a blanket over it, not a powered blanket, but just an insulating blanket. And that trapped enough of its generated heat to allow it to accelerate to where they could be driving on it the next day.
Yeah, that's awesome. Yeah, because I read somewhere. I haven't done bridges in my career, but I read the one issue they have is when they need to repair a bridge or a road or whatever. Like you said, you clean out the damaged parts, you chip out the old concrete. If you're not using UHPC, you're using regular concrete. And my understanding is if there's a difference between the strength of the old concrete and the new concrete, that could be problematic. It can actually cause, I guess, cracking and all kinds of stuff that you don't want to happen on the repair. So it sounds like UHPC, you're doing the same thing, but you're not having any concerns about the difference between the existing concrete and the UHPC. It's just a whole different type of material.
You nailed it. No, you're not only following, and I wish I could bring you to some pre-meetings with contractors. You just nailed what it's about, Seth. One is the thickness and mass. If you're using regular concrete, overlaying could be 5, 6, 7, 8 inches. Number one. Number two, the bonding characteristics of UHPC are outrageous. The particles are so small. Some of them are submicron, nano, and they're going into things that you and I don't even see, little scratches and nooks and crannies. The other thing is the expansion contraction coefficient. And so we have bond, expansion, contraction capability. And then we have that tensile strength. when I mentioned tensile as one of the biggies, it's much more than just being able to bend it. That tensile, and I can't speak too much to it today. Hopefully I will the next time we speak. But tensile has so much, I'll just use the word impact resistance. It has so many benefits to connecting UHPC to existing materials, whether it be steel, plastic, wood. I've experimented with asphalt roofs, concrete, whether it's old, new, 5K, 3K, KSI. The stuff bonds amazingly because of its tensile capabilities and because of those fibers, that fiber matrix, it gives. One way to look at it is almost like a hardwood floor in your house. That thing is living, it's moving, it's breathing. You put a new hardwood flooring, you don't come in and butt it to the wall, you let it acclimate. Now that's for moisture offsetting, but concrete bridge is the same. But by putting on this material that has these tensile abilities to adapt and adjust, that doesn't shrink that much, relatively speaking. It shrinks, but not that much. Then has the bond that it has. It's a nice marriage.
Yeah.
A really nice marriage to just about every material.
Yeah. I wonder if this is a good segue to the Shotcrete. Do you want to talk about that?
Sure.
Oh, so when you said that, now that I'm looking at your message and connecting the two. So you could tell me what you're doing with Shotcrete, but the first thing I thought of was you're shooting this stuff up against different material, right? Or something like that?
Yes, sir. Yes. I will. You may have saw on one of my posts, but that is correct. We did a shelter in Chattanooga, Tennessee. We've done a design beam by Cherie, a great professor who is semi-leading along with a couple other handful of professors, and Ben Graybill at the FHWA, and Zach Haber down in Florida, and Rafiq. There's just so many people that are constantly proposing academic ways to prove these things. We pick up, thanks to them, and we turn it into a physical representation. Case in point, we're in Chattanooga. They wanted a shelter that was basically tornado, hurricane weatherproof, but could be erected quickly and would provide a quality of life for the people that would be in it. So they basically took a rib of 3D printed, like a big 3D printed matrix. Then they filled it full of foam. Then they shaved it off. So you basically had this 4-inch wall with an incredible R rating, and they put it on a platform, the floor. Then we came in and shot about an inch of material over the whole thing. And it's just, A, it's so logical. B, it was bolted to the ground. It's just a beautiful piece. And that was done with shotcreting. Why wouldn't you spackle it? Because it's a non-Newtonian fluid, because it has thixotropic properties. You could do it, but if you've ever played around with decorative concrete and you're trying to, or spackle, and you're trying to trowel up, you trowel up, 50% falls down. You trowel up, 50% falls down. Eventually it sticks. But every time it's falling and stuff, it's losing some of its water and characteristics. When you're spraying UHPC, nothing could be better. It's atomizing the water in the air. So it goes from a liquid to a gas back to a liquid over a 12-inch period. So you're pumping the material. In order to shotcrete, you got to be able to pump. And then it's at the nozzle and it's being pumped and pushed like a heart. And then you have to inject air to atomize it so that it sprays. When you see spraying, very little of it has to do with the pump. It all has to do with the air injection. The pump has to keep up with supplying the material that then gets sprayed or turned atomized by the air. Then it hits the wall. What they're finding out is the characteristics only improve when you shotcrete UHPC. The challenge of it, and why it took 3.5 years and a lot of R&D funding, the challenge was the metal fibers and the thickness and density of this material. If you just go and you just rent a concrete pump, the ones that go 30 stories or the ones, cute little things that make a wheelbarrow's worth and they pump, and you try to pump, you have a lot of internal parts. You have ledges. You have things touching the concrete internally. And now you have these god-awful although they work. Hypodermic needles that are 300,000 psi tensile strength, they don't bend, is my point. Now you're trying to pump that thing through with a very low water cement ratio. First thing you're going to get is friction, which means you're going to get heat. I mentioned earlier that UHPC loves heat once it's placed. So you can get into a situation where it clogs, it only works for a while. And then when you're all done, it could take 6, 7, 8 hours to clean it, because you don't want UHPC sitting in there for a half a day. It's over. You're going to throw away your thing. So we basically paid homage to an existing technology, a squeeze pump, but we had to modify the heck out of it to make it not fail. The first one we bought off the shelf clogged up in about 5 minutes. 4 years later, it works. We run it all day long. We did bridge joints for pumping in Illinois, and we did the shotcreting, the spraying at Iowa State University, and we did the shelter down in Chattanooga, Tennessee. No problems. Everything went well. So we like spraying when it makes sense to do it, just because you can. I have guys now, contractors, saying, we want to spray. I'm like, why? Because we want to spray. And you got to have a reason to do it.
So are you thinking the spray is going to be for structural repairs, like vertical applications, or what are you thinking with it?
I'm thinking hardening, whether it be nuclear power plants, whether it be the spark plugs on electric plants, hardening. I'm thinking protecting, encapsulating, restoring. You got a bridge, and it's just rusting. But the majority of that metal is still intact. 60, 70, 80% of it is still fine. You're not going to rip the girder out and redo it. You could spray layers of this material, sandblast it, spray layers of this material, and just like laminates are with wood, multiple layers are stronger than one thick coat, and you got yourself an encapsulated, fossilized, hardened, strengthened steel girder. You could spray buildings with it. You could spray anything your imagination can think of as far as spraying. And let your mind, everybody on the podcast, just think of something that could realize an advantage by having a tensile, flexual, extremely high compressive strength material with all the characteristics Seth and I have been talking about. It could be a balloon. We took some composite bar as a proof of concept. We bent it, stuck it in the ground, basically made what looked like a skeleton to an igloo. We went to Home Depot and stretched a bed sheet over it. We sprayed it. We sprayed 3 or 4 lifts about a 1/4 inch thick. 2 hours later, we could stand on it. The next day, you couldn't break it with a hammer. So let your imagination run wild with preservation, restoration, and hardening. And that's what you can do with it.
Yeah. That sounds pretty cool. I think this is a good spot to end today. Do you think we captured everything you want to talk about today, and then you're going to come back here in a few months and share the other stuff you're working on?
Yes to that question. I don't think Seth, you and I could go for hours, but sound bites are the best. We covered everything you and I agreed to try to cover today, but I'd welcome the privilege to come back and expand on some of the things I wasn't able to disclose today.
Yeah. No, that Shotcrete part, I think your timing is fantastic, because I think we're going into a period of restoration and renovation and repair. If folks want to reach out to you, Bill, what's the best way to reach out to you?
Bill at Steelike, STEELIKE, or just steelike.com. STEEL, the word steel, IKE, one word, one L. And that's the easiest way to get me. Or reach out to Seth.
Thank you, Bill. I appreciate that. Yeah, anybody that's on the podcast, if you're having a hard time, get a hold of them. Get a hold of me. I'll chase them down for you. All right, Bill, thanks for doing this again. And folks, until next time, keep it concrete.
Excellent. Thank you, Seth.
And that concludes another episode of the Concrete Logic Podcast. I hope you got some value out of that episode and learned a thing or two. If you did,
visit our website, concretelogicpodcast.com, click on the show support tab, and learn how you could be listed as a producer of an episode. Again, that's concretelogicpodcast.com. Click on show support tab to learn how you can support the show. And as always, Mike Dunton will take us out.
That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for a dollar, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or two. Expect more, it's written in our blood. With wood, iron, and mud. From the swamps to the city, from the Lone Star heat to the woods of the Georgia pine. Good old boys and girls who ain't afraid of getting dirty for a clean time. And if you want to see the fire in a grown man's eyes beneath the hot summer sun, find the wild-eyed boys clocking days and nights, working hard to get that job done with wood, iron, and mud. We work hard for a dollar, give thanks to the Lord above. The color of our collars ain't white or blue, we're all gray collar through and through. Expect more, it's written